We have an example problem here. We have a circuit. It has 2 batteries, 3 resistors. The problem itself asks us to determine the magnitude and direction of the currents through each resistor. Okay, because we have these 2 batteries, there's no way to follow a path. I mean, we could follow this path to get to the other side and say the 10 and the 15 are in series, but that would not be quite right because we have a choice to come up this way, and then there's another battery here. So there's not a way to determine an equivalent resistance for this circuit. Just any problem you see, multiple batteries, not in the same branch, we will need to approach the problem using Kirchhoff's rules or laws. So the 2 laws, one of them is the junction rule or law that tells us that if we add up all the currents flowing in to a junction, they have to equal the summation of the currents flowing out of the junction. That has to do with the conservation of charge. Whatever charge is moving must keep moving. The second law is the loop law. And that's where we're looking at potential differences. If we add up all of the delta V's of every single element as we pass and travel a loop, then if we get back to where we started, they need to add up to be 0. Okay. So any problem where we're using Kirchhoff's rules or laws, we always have to write one equation describing the junction law, and typically we need 2 equations from the loop. So one equation is going to come from junction, 2 equations from the loop. The first thing I do when I am solving a problem like this is I draw currents into each branch. So for example, this 12-volt battery, I know there's going to be current flowing out of positive, but also in to the negative side. So this current, I'm going to call it I1. You can call it whatever you want, but we need to distinguish that from the currents that will be in the other branch. So currents will flow from junction. A junction is where we have 3 wires or more to junction. So I draw I1 only from junction to junction. I don't pass through the junction with I1. And that's because I1, when it reaches this junction on the left side, it could potentially split into a 2 and a 3 current, right? There's 2 wires, 2 paths for it to take. I base the direction of my current off of the battery that is in the circuit, that's in that branch. So using the traditional definition of current flowing from high potential to low, that's why I drew it coming out, so to the left, out of the positive side, and flowing towards on the right side, so to the left. All right. I'm going to draw the current in this bottom branch next. It would come out of positive into negative. So this current, I'll just call I2. I don't know the value of these currents. That's what I'm asked to find. Now I3 is going to be the current through the middle branch. Since there's no battery, I really can't say right or left based off of a battery in the middle. It turns out, as long as I'm careful in writing my equations and going through the algebra, it doesn't matter which way I draw that current. I am going to choose to draw the current left to right only because of this 12-volt battery being bigger. I'm going to assume then the current I1 is bigger than I2 because that's a 9-volt battery. So if I'm wrong, that's okay. I will find out from my math. But we want to have a current drawn in every branch. So every wire, junction to junction. That current, that direction is important in terms of writing out our junction law equation, but it is also important in terms of determining high and low potentials when we write out our loop laws. Okay, so our junction equation. It doesn't matter which junction we look at here, we just need to look at one of them. So for example, if we look at this junction on the right, to write the junction law equation, when we say IN, I mean, okay, look at the arrows. We've drawn arrows to represent the currents. Which of those arrows point towards that junction? Well, I see I2 pointing towards the junction. I see I3 pointing towards the junction. But I1 has to be pointing away to come up and point left into this battery. So my equation would be I2 plus I3. Those two currents are coming towards the junction. They have to equal the currents flowing out. In this case, we only have I1 flowing out of the junction. So we have an equation here that relates the current values. However many amps I1, I2, and I3 are, I2 and I3 have to add up to equal I1. So this equation will be one of the equations we need to use to, solve the problem. And by the way, just really quick, if you look at the junction on the left side, I1 is the one coming into the junction. I2 and I3 point away, meaning they're coming out of the junction. We get the exact same equation, just a different order in terms of what was in versus out. And that's why we will only need one equation. In your EE courses, you may very well run into more complex circuits. Here, our circuits will lead us to needing one junction law equation. Okay, loop law. Technically, there's 3 loops in this circuit that we could do. We could look at just the top loop going around the 12 through the 10 and then the 5. We could do the bottom loop. That would take us through the 10, the bottom 5, and the 9. Or we could do the outside loop, where we go through the 5, the 9, and then the top 5 and the 12. We have 3 unknowns, so we only need 2 more equations. So we don't need to do write out all 3 loops. Maybe I will write out all 3 though, just for practice sake. Okay, loop rules. Loop law, loop rules, we're looking at potential differences. Meaning there's a delta V for this resistor. I'm going to call it delta V1. This resistor has a delta V. I'm going to call it delta V2. This middle resistor will have a delta V. I'll call it delta V3. Whether we add or subtract these delta V's is based off of the direction we're following our loop. Since we're using the traditional definition of current though, current always flows from high to low potential. So for any of these individual resistors, like the top resistor, since I've drawn the current pointing to the left, That means high to low, the left side has to be the low side in terms of the potential. This 10 ohm resistor in the middle, current flows high to low, the arrow points to the low side. So the right side for the 10 ohm resistor would be low. The other side, the left side, would be high. For our bottom 5 ohm resistor, we have current drawn to the right. This right side has to be low. The left side then will be high. So that's just based off of the traditional definition of current. It would be the same as the electric field. Okay, loop rules. Let's look at the top loop since I already wrote top over here on the left. The main requirement for the loop rule is that we start and end in the same place. It does not matter where we start and end, except for they just have to be the same point. So for example, for the top loop, just to pull out a point, let's start at this top left corner, which means we also have to end our loop at this top left corner. We do not have to follow the current. Sorry, I'm trying to write end and it's not showing up very nicely. And there. Our loop, we can either go opposite the current or with the current. It doesn't matter. The only requirement is we start and end at the same location and account for increases and decreases of potential differences. Okay? So let's take our loop and go to the right. So I'm starting at this left corner and I am taking my loop to the right. The first thing I am passing by is this battery. Since I am traveling in a direction that takes me from the high potential plate to the low potential plate, I'm going to see a drop. So down on the left where I'm writing my equation, I'm going to see right, I have a drop. I'm seeing a drop of 12 volts. I'm not going to leave the V though, just the 12. But know that represents the voltage of the battery. It's a drop simply because the path I've chosen to take is to the right, which means I see this negative plate last. I saw the positive plate first, I saw the negative plate last, so I see a minus 12. As I keep following my path, the next thing I pass by is resistor 1. So the potential I'm seeing is delta V1. The sign I want is the last of the signs I see. Since I'm going opposite the current, I see an increase, so a plus. So I've added that to my equation down here on the left. So I saw a drop of 12 volts from the battery, but I'm seeing an increase of whatever delta V is, delta V1 happens to be. Okay, I have to keep following my path. My path, I don't want to confuse this. My path is going to the left through the middle. So as I go to the left through the middle, I am going opposite the current, so low to high. So I'm going to see an increase of delta V3. So if my path takes me opposite the current, I see an increase of potential for the resistor. My path, my requirement is that I get back to where I started. As soon as I get back to the top left corner, because that's where I started, then I finish my equation by saying equals 0. Now, one other substitution I want to make is that, so for resistors, we know the potential difference across a resistor is I times R. So in place of delta V1, since that was for my top 5 ohm resistor, the current flowing through that resistor is what I labeled as I1. The resistance is 5 ohms. So this is I times R for V1. Delta V3 is for this 10 ohm resistor. The current I have drawn flowing through it is I3. The resistance is 10 ohms. And to make it a complete equation, I do need equals 0. So what this tells me right now is that 5I1 plus 10I3 has to equal 12. So we have another equation. This one is in terms of just I1 and I3. Our junction equation is in terms of I1, I2, and I3. Since we have 3 unknowns, we need one more loop. Okay, let's look at the bottom loop. I'll go ahead and write all 3 just for practice sake, and then we'll solve with just 2 of them. So again, loop. We have to start and end in the same location. It does not matter where we start, but we have to end where we started. Let's go ahead and just start this loop in the bottom left corner. And let's take this path going to the right. We don't have to go with the current, but we can. So in this case, we're going with the current. We're going to see a potential difference of delta V2 is what I've called it. But because our path is taking us from high to low, we would see a decrease of delta V2. So minus delta V2. As I keep going, the next voltage I see is this 9 volts. Because my path is to the right, I'm going from low to high. So I'm going to see an increase of 9 volts. I have to keep following my path. Since I'm doing the bottom loop, I'm going to turn down the middle. Now I'm going through this V3, this 10 ohm resistor. I'm headed to the left, so I'm going low to high. It's an increase. Since I'm going opposite the current, an increase of delta V3. I keep going, make sure I get back to where I started. So now I'm ending here, so this equals 0. For V2, it's a resistor, so its current times its voltage would be its potential difference. The 9 volts already is a voltage, that was the battery. Delta V3 is the current I3 times the 10 ohm resistor. So we have another equation here that tells us that minus 5I2 plus 9 plus 10I3 has to equal 0. Now, technically, we can solve the problem because we now have 3 equations and we have 3 unknowns. I want to go ahead and just write out what the other loop would look like, the outer loop, just so you can see. We won't use all 3. We'll use whichever 2 are most helpful. So outer loop, I can totally start and end wherever I want. If I start at the bottom right-hand corner, Let's go ahead and just go counterclockwise again. Let's go with I2. So our path is going up, 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 up. We keep going. The first element we're going to pass by is this top 5 ohm resistor. Since our path is taking us towards the left, we're seeing this negative end, this lower potential end last. That means I would start my equation down here as minus delta V1. I'm seeing a drop because I'm going with the current. You can totally memorize that part. If you're going with the current on your loop, then it's going to be a drop. As I continue this path, I'm still going to the left, which means I'm going from low to high as far as the battery is concerned. So I'm seeing an increase, so plus the 12 volts for the battery. I'll put the units on for a sec. Okay, I continue my path. The next element I pass by is this bottom 5 ohm resistor. Since I'm going with the current, I'm seeing that drop of delta V2. I pass by this battery. As I pass by this battery, I'm going low to high. So I'm going to see an increase of 9 volts. That gets me back to where I started. So I can now say this equals 0. I would still want to make these substitutions that delta V1 is going to be the current flowing through this resistor, which I've called I1, times that resistance of 5 ohms. So the 12 is already a voltage. V2 is for this bottom 5 ohm resistor, so that's going to be the current flowing through it, which I labeled I2, times its resistance, which is 5 ohms. And then plus the 9 volts, that already is a voltage. So those have to add up to be 0. So we have minus 5I1 minus 5I2 plus 21 have to add up to be 0. So we have 4 equations now. We only need 3. It turns out we cannot use all 3 loop equations. They're not linearly independent. What that means is if I took equation 1 over here and substituted into equation 2, we would actually get equation 3 here. So we would end up, if we tried to use only loop equations, we would end up proving that 1 was equal to 1, which is not helpful. Okay, the math. The algebra. If you've had linear equations, know how to use matrices, you can. This particular problem, we just have to do a little algebra. What I'm going to do the algebra. I am going to take I1 here, which I know is I2 plus I3, and I'm going to come over to equation 1 and plug that in. So just substitution. I could easily plug it into equation 3. There's no real reason why I'm choosing 1 over 3. So plugging in the junction equation. This is just a system of equations. You have solved systems of equations before. So I1, I'm going to put I2 plus I3. And then as I finish the equation, I now have 5I2 plus 5I3 plus 10I3 equals 12. So 5I2 plus 15I3 is 12. So now I have an equation that is in terms of I2 and I3. Notice equation 2 is also in terms of I2 and I3. So let's use these two now. Since I see 5i2 there, I'm going to solve for negative 5i2 here. So minus 5i2 would be 15i3 minus 12. So I took this to the other side. The reason I'm going ahead and just solving for negative 5i2 is because I see minus 5i2 right here. So I'm plugging this in for the minus 5i2 part. So 15i3 minus 12, and then finishing the equation, we have plus 9 plus 10i3 is equal to 0. I can combine the 15 and the 10, so 25i3 minus 3 equals 0. So 25i3 equals 3. So i3 will be 3/25, which I'm going to put in decimal form. 0.12 amps is what I3, the value of I3. Okay, we now have one value. We still need I2 and I3. But now that we have I3, we can come back to any of these equations, actually. So if we come back to equation 2, if I have I3, I can put here 9 plus 10i3, which I know I'm going to plug in I3 in just a minute. I'm bringing the 5i2 to the other side. So if I just divide by 5, this will be I2. So I2 will be 9 plus 10 times the 0.12 we just found for I3 divided by 5. So I'm getting 2.04 amps would be I2. Well, I1, we can either come back to equation 1 or just come back to the junction rule. I1 is equal to I2 plus I3, so 2.04 amps plus 0.12 amps, so 2.16 amps would be I1. Now, revisiting the question really fast, I'm just going to scroll up for just a second. This problem asked us for the magnitude and direction of the currents through each resistor. So we chose directions of currents. We drew those in first thing. Assuming all the algebra that has been done here and the equation setup that has been done here, getting positive numbers for these currents means they are in the direction I drew them. Had I drawn one in the wrong direction, then I would have come up with a negative answer. And as long as I had set up my equations properly and based my plus and minuses off the circuit properly, that minus sign would simply mean that that current was in the opposite direction. Not all problems are going to require this much algebra. Some of them will. If you don't know any of the currents, those are the ones that typically require more algebra. I'm going to do a couple more examples as well where you will see the algebra is a bit easier or less algebra, I guess, maybe. So just less steps to get to answers. But the approach will be the same.